Welcome to Lesson 30. Today we're going to continue with our sequences and series that we started in the last lesson, but now we're going to look at the different style. We're going to look at geometric sequences and series. Now to start out with, you might want to take just a moment and read through this problem. I think this is a good one. So we're giving an injection of 20 milligrams. Well, we're not a doctor or nurses. And the next day, only 50% of that is going to remain. But this is kind of a half-life idea in that theoretically, this medication will always be in the patient's body. Okay, so I said write a series that represents the amount of the drug present in the patient's body each day. So for the first day, we're going to assume that the patient has the 20 milligrams that was injected. But now to find out how much is in the second day, we would take the 20 for the second day, plus they have half of the 20 left over from yesterday's injection. So I think 20 plus 10, we end up with 30 milligrams as the amount of medication in the patient's body on that second day. Well, now on the third day, the patient gets a new injection, plus they have half of the second day's injection in there. And do you realize that they have a quarter of what was put in on the first day? Because you know, each day what was in there, half of it has metabolized and then half of it is still present within the body. So by the second day, after 2 days, only a quarter of that is going to be left. Okay? So let's see here on that third day, and watch these numbers as well. I think this might help it make sense. You have 20 milligrams for the new injection. Then 10 milligrams left over from yesterday's injection and 5 milligrams left from the very beginning. So that gives us a total of 35. Okay, for the fourth day. Well, on the fourth day, we're going to have half of all of this plus another 20 in a sense. So we have the new injection. We have half of yesterday's, a quarter of the day before's, and an eighth for the previous day. Are you with me still? So we have that 35 milligrams already in the body, and we have, let's see here, an eighth of 20 would be 2.5. Another 2.5 milligrams in there. So we have 37.5 milligrams of that medication. And you know what's kind of interesting is if you think of what this might look like if you graph it, you go from having none to 20, you've got a big increase there at the very beginning, and then you increase to 30, but then you're increasing a little bit less each day with how much is in the body. So I think that as you look at this over a long term, it could be a very interesting problem. Okay, and we will come back to this problem. Now I asked how much would be present after day 5, and we have day 1, 2, 3, and 4, so we've got to go one more time. And I think you can see the pattern that's going on here. Technically, what I'm doing is adding on the very first day because we've got the new injection, half of yesterday's, a quarter of the days before, and we go all the way down here to 1/16 now of the very first day's injection, which would be 1.25 milligrams. So adding that 1.25 milligrams on, we've got 38.75 milligrams then as the amount of medication in the patient's body on day 5. And I think you can see what's kind of happening here, that we're going to kind of settle in towards a value, and we will come back and revisit this particular problem. But then I have a question. It's going to pop up right here in these numbers I wrote. How is this series different from the ones that we worked with before? Well, unfortunately, that hasn't come back up here, but you'll notice that what I had written was 20 plus 20 times a half plus 20 times a fourth plus 20 times an eighth plus 20 times 1/16. And the question would be, am I adding a certain amount to go from term to term in this sequence? And I think the answer is obviously no. I'm multiplying. You might realize that you take 20 times 1/2 to get to here, multiply this times 1/2, this times 1/2. Oh, so what we're doing here to go from term to term is actually multiplying by 1/2. That's what makes this guy geometric. Okay? So, there's your first introduction to a geometric sequence. And I said, let's write out the first 4 terms of this particular sequence. Now remember from the previous lesson that this is saying the nth term. A sub n is the nth term. So if I want the first term, I let n be 1. Okay, so for the moment, n is going to be 1 throughout this equation. So I have 3 times 5 to the 0. Well, 5 to the 0 is 1, so our very first term is 3. Now, to get the second term, I would have a sub 2 is 3 times, now remember, that means the n is temporarily 2 throughout this whole equation. I'd have 5 raised to the 2 minus 1, or the first power, and that gives me what, 15? I believe. Okay. Then to get to the third term, and I hope you're really paying attention to this notation because I want you to be comfortable with it. This is saying my third term. And this describes how to find that third term. It's going to be 3 times 5 squared. So I believe we have 75 going on that guy. Yeah? And one more, we want a sub 4. That will be 3 times 5 to the third. And I believe, let's see here, that's 125 times 3, 375, I think. Now the question is, can we find a sub 7 for the above sequence? Now we're going to get to the formulas, but I want to get to the formulas by having you use your common sense and go there with me so that it makes total sense what we do to find these things. To find my 7th term, now pay attention to what we've done. Actually, I apologize. All we need to do is put in the 7 here. So we would have 3 times 5 to the 6th. Getting ahead of myself. Well, you know what? I don't know 5 to the 6th off the top of my head, so I asked my calculator what that happened to be, and 5 to the 6th is 15,625, so my 7th term is this 46,875. Okay? And how am I getting from term to term? Well, remember what those terms were? We had 3, 15, 75, 375. How am I going from here to here? Multiply by 5, multiply by 5, multiply by 5. And if I'm multiplying each time, by the way, that makes sense from the formula right here, the continual multiplication of 5, that means he's geometric. Okay? Find a sub 10. Well, let's see here. All I have is a listing of numbers. And what do we call a listing of numbers? We call it a sequence. Okay. So you might ask yourself, well, what would I add to 2 to get 6? Well, I would add 4. If I add 4 to 6, do I get to 18? And you say, no. All right. What that means, my eraser still doesn't work, is that he's not arithmetic. So I say, all right, he's not arithmetic. Well, what would I multiply times the 2 to get to 6? I'd multiply times 3. Well, 6 times 3? Yeah. Okay. So that means that this guy is geometric. Now, I'm asked to find a sub 10. And I could just go ahead and go term by term, times 3, times 3, times 3. But I'm thinking there's got to be a better way. So let's think. How do I get to that 6? Well, I started with 2 and I multiplied by 3, right? Well, how do I get to the 18? Well, I started with 2 and I multiplied by 3 twice. So to get to the 10th term, I'm going to start with 2 and I'm going to do what? I'm going to multiply by 3. Now, you have to ponder this for just a moment. How many times will I multiply by 3 to get out to the 10th term? Well, I multiply it once to get to the second, twice to get to the third term. So you realize, oh, I'm going to multiply that times 3 to the 9th. And again, I didn't want to do that arithmetic, so I said, what is 3 to the 9th? There we go. There is my 10th term, and I was able to jump right out there to that 10th term. Well, let's try it again. New sequence. And take a second. Am I adding the same thing to go from term to term? That's not likely when you're bouncing back and forth between positives and negatives. Am I multiplying? Well, you might say I'm dividing by 2, and dividing by -2 alternates those signs. But of course, dividing by -2 would be the same as multiplying by -1/2. That's multiplying times -1/2, multiplying times -1/2. There we go. Okay. So now that I know what the pattern is, I want to go to the 9th term. Okay, well, let's think about this. To get to the 9th term, I'd have to start where? Well, I start at the beginning. And the very beginning of this sequence is 24. And then what do I do to go from term to term? Well, I'm multiplying. I'm going to keep multiplying by -1/2. And then the question is, well, how many times will I multiply by that -1/2 to get out to my 9th term? And again, you want to really think about this so that you're comfortable with this idea. To get to the 2nd term, I've multiplied once. To get to the 3rd term, I have multiplied twice. So you always are lagging one behind the term that you're looking for. You know, we did the same exact thing in our arithmetic. We added on one less common difference than the term we were looking for. Try to find those connections. It makes it easier when you put everything together. Well, let's see here. Let's go ahead and do this arithmetic just to see what he looks like. Well, that would be 24 times, well, a -2, an even power. He's going to go positive. And I have 1/2 to the 8th. And I believe that's going to be 3/2 to the 5th if I do some simplifying. And we should get a 3/32. Okay? And of course, on these beginning problems, if it would make you feel more comfortable, go ahead and take your calculator and actually write down all of these terms till you see that particular term, just so that you can have your comfort level up there. Well then, for geometric series, how do we get to the nth term? You know, we like to have these formulas because then we can just grab that formula, or I can put it into a spreadsheet if I'd like. Well, remember that what we do is we start at our very first term, right? We start at the very first term. And then we're going to multiply on some amount. Now, what most authors use as the letter here for that amount we multiply on, they generally use the letter R, and that's for the common ratio. The common ratio is that amount that we're multiplying on each time. Like in the very last problem, it was that -1/2. And then, let's think about this. How many times do we need to multiply this common number on to get to the nth term? Well, remember we were always lagging by 1. Yes? Okay. Now to get this S sub n formula, now what that means, I hope you remember, because we talked about that with our basic sequences and we've talked about it with our arithmetic sequences. This is called the nth partial sum. Nth partial sum. Meaning we're going to add up the first n of these. All right? Now, we haven't done any of the addition here because unlike the arithmetic, do you remember the little story about Carl Gauss adding up the first and the last and doing that very quickly? Well, that works out lovely for those arithmetics. The geometric is not quite as easy to just have an insight to the sum. So what I'd like to do is take a moment and derive this formula for you. I know, that's a scary thought. But the reason I do is that it's very easy to mix up this formula, and I actually do derive it for myself sometimes just to make sure that I get everything in its place. Okay. So here's what we're going to do. Let's first write down what this S sub n would actually mean. He would be the first term, plus, for the second term, I would have a sub 1 times r. Would you agree to that? The first term times my common ratio, that's my second term. And to get to my third term, I would multiply by r again, and then I multiply times r again, and I just keep doing that for a very long time. Okay. Now remember, how many terms am I adding up if this subscript is n? I'm adding up n of them. Okay, so what is the nth term? I'm going to leave myself some space here, and I'm going to say, okay, to get to the nth term, well, you know we can reason it all out, but we also just wrote down how to find the nth term. It's a sub 1 r to the n minus 1. Now, sometimes when we're doing this derivation, we're having to work with this complicated formula. It helps to see the next to the last term. So that would be a sub 1 times r to what power? Now you see we have it to the 0th, 1st, 2nd, 3rd. They keep increasing. And this last guy is n minus 1. So what would come before n minus 1? Well, it would be n minus 2. Oh, I know this is kind of scary, but stay with me, okay? Because the more you see this kind of thing, the more comfortable you will be with it. Well, here's the only thing that you have to kind of remember gets done in this derivation. Multiply all the way through this equation times r. Now you might say, why would I do that? Be patient, you'll see where it gets us, okay? Now, if I'm going to multiply through by r, that means on this side I essentially distribute the r. So I would have this term times r, and what I'm going to do is place him right underneath this term. That's why I left a little bit of space there. If I multiply a sub 1 times r, this is what I get, and it just makes sense to kind of line up like terms. When I multiply this term times r, won't that give me an r squared? And when I multiply this term times r, I will get an r cubed. And I'll get an r to the 4th and an r to the 5th and so on. Now when I multiply this term times another r, do you realize it increases this exponent? Well, that's going to go to r to the n minus 1. And multiply the last term times another r, and I get a sub 1 r to the nth. Okay? And there's all this dot, dot, dot in the middle. You know, I can't fill in the middle because I don't know how big n is. Well, then here's what's very clever about this process. I am now going to subtract these two equations. Essentially, what I'm going to do, because subtraction can have us making mistakes, so I'm going to multiply through by a negative 1, and then I'm going to add. And look at what beautifully happens here. On the left-hand side, I get s sub n minus r times s sub n. And on the right-hand side, I get an a sub 1, because I didn't have any like term to subtract there. But then look at what happens here. Those guys cancel, don't they? These guys cancel. These cancel. Oh, and look. What happens is all this dot, dot, dot stuff in the middle is all going to cancel out. That's why we multiply by an r, because everything will cancel out except the very first term here and the very last term over here. So I have a sub 1 minus a sub 1 r to the nth. Wow, that was a huge help to us. For one thing, it got rid of that whole middle section that I couldn't deal with. Now I'm just about done. I look at this and I want to get the s sub n by itself. So what I do is I factor the s sub n out of these two terms. And that would leave me with 1 minus r. Okay. Then divide your 1 minus r off. S sub n is equal to a sub 1 minus a sub 1 r to the n all over 1 minus r. That was fun, wasn't it? Well, you should see those. And I understand that you don't necessarily feel comfortable with it, but maybe after you go through it a time or two, you might understand, hey, that's really pretty cool. One last thing I'd like to do is say, sometimes you see it with this a sub 1 factored out of the numerator. This is probably the more common way that you see it in some textbooks. But anyhow, you could see either of these formulas for the sum. Now, I think this is kind of a hard one to just remember unless you're a very good memorizer. And so that's why I like to be able to derive it, because it doesn't take that long. And if you can deal with the algebra, it's not that difficult. And right there then is my sum formula. So here's what we've got. You have two new formulas to deal with here. How to find the nth term and how to find the sum of geometric sequences in series. So add this to the two that you got in the last lesson with arithmetic sequences in series, and then you'll have one more to go. So now let's actually use that formula to find s sub 10 in this series. Hey, do you remember the difference between a series and a sequence? And I've tried to be careful. I hope I've always used them properly. Series is when you are adding those terms of your sequence. The sequence is just the listing. Okay, so to find S sub 10, let's come over here. I'm going to say S sub 10 is, what's this A sub 1? It means your first term, because A sub n is what we use to denote the nth term. My first term is 2. Now, what is an R? R is that common ratio, and that's what's being multiplied each time. Now, I apologize that I didn't go back and just reiterate how are we getting from term to term? Because we've seen this one. We're multiplying by 3. We're multiplying by 3. You want to make sure before you apply the formula that you have the correct type of sequence to use that sequence or series. My common ratio there is 3. Now be careful. To what power am I supposed to raise it? To the nth power. And n is set right here by that subscript. So I need to raise it to the 10th power. All over 1 minus 3. By the way, it's not uncommon that you will end up with negative numbers on the top and the bottom here. Just be very, very careful in how you handle them. Now, I'm cool with 2 to the 10th, but 3 to the 10th is not something that's just stuck up there in my mind, and so I decided to have that preset. We have our formula set up here, rather large number, okay? And you know what? I decided that I would allow myself to do the arithmetic at this point in time because it's really kind of cool arithmetic. Of course, cool to me isn't necessarily cool to you. Coming from the pre-calculator days, I would say cancel these 2's. Now notice this was a negative 2, so this is going to be negative 1 times that, which simply means I have 59,049 minus 1, because this would go positive, this would go negative. My sum is 59,048. That was kind of cool. Okay, to get S sub 10 for this series. Now you'll notice that he's alternating plus and minuses, but what this technically means, you know from pre-algebra days, these are plus negatives, right? And this is the exact same series we saw on a previous screen. We are multiplying by negative 1/2. We are multiplying by negative 1/2. So that means we have what kind of series going on here? He's not arithmetic because you add to get from term to term on arithmetic. This guy is geometric. And if he's geometric and I want the sum, I use the S sub n formula right here. Okay? And note, this n is going to be very important, and my n is 10. So, S sub 10 is going to be my first term, that's what that A sub 1 is, times 1 minus, you have to put that minus in, that's part of the formula. 1 minus my common ratio raised to the nth power, all over 1 minus my common ratio. Okay. Now, I was just grading some tests of students doing this, and they had a tendency to make sign errors down here. Just kind of ignored the fact that that was negative. You know from a long time ago that minus a negative becomes plus a positive. So we have a 3/2 down in the denominator. Okay? And in the numerator, I've got 1 minus, and this is going to go to a positive value because I have a negative raised to an even power. And 2 to the 10th is 1,024, just in case you didn't know. Okay. Now to do the arithmetic here, I can, this is a division by 3/2, so I can multiply by 2/3. So I end up with 2/3 times 24 times, and if you can't handle this, do it on a calculator that does fractions, but it's going to be 1,023 over 1,024. Because you don't have one whole minus one little 1,024th. Okay. And I think I can do some canceling here. That leaves me with an 8. And I get 1,023 over, let's see here, this is technically 4 2s. I shouldn't have multiplied that out. I think I get a 64 in the bottom. You can double check my arithmetic. But 1,023 over 64 is this sum. I always like to go back and see if my answer makes any sense. And my first thought is, well, good gracious, how did I get fractions? You know, because right now, if I just add and subtract those numbers, there aren't any fractions. But do you realize that the very next term has a fraction? The very next term is going to be a 3/2, and then we have, a 3 over 4, and then a 3 over 16. So yes, it does make sense that we ended up with the fraction. Okay? Now, I told you we'd go back and revisit our medication problem from before. What if that patient is going to be on this medication for a long, long, long time? And I don't know if you realize it, and I am not an expert. I don't know biology well. I don't know medicine at all. But it does kind of make sense that there are some medications that may stay in your body for a very long time. You may see traces of it. And so in this particular simplified version, we're saying half of it is remaining from time to time, and we'd like to know, well, what happens for the rest of your life? Well, that's kind of interesting as to what's going to happen here for the rest of your life. If I start to write out some of the terms on this guy, by the way, doesn't this notation just make you feel really, really smart? Or it scares you to death, one or the other. Let's take this very slowly. What does the sigma mean? Sum. And what is this k equals 1 on the bottom? That's where your k starts. And this infinity sign on the top, that's where it ends. So let's start writing out some of the terms. If k is 1, we have 1 minus 1, which is 0. Anything to the 0 power, except 0, is 1. So my first term is 20. Okay? Now for my second term, put in a 2. 2 minus 1 is 1. 20 times a half is 10. Okay, and we did this before. We have plus 5 halves, plus 5 fourths. I wrote these in decimals before, but now I'm writing them in fractions. You notice that what's going to happen is this term is just going to keep getting smaller and smaller and smaller and smaller. But how in the world do I find the sum if this just goes on forever? Well, it helps once you get into calculus and kind of get some good ideas about some things, but I want you to come to this formula for just a moment. If your ratio is really small, well, 1/2, it's not really small, but we'll use that. If your ratio is 1/2, and you raise it to the 1,000th power, you might even try that on your calculator. Then you might try, what if I take it to the 10,000th, to the 100,000th? You know, at some point in time, your calculator is going to tell you that this answer is 0. Now, you and I know it's not 0, but your calculator got to a point where it said, uncle. All right? because it got so extremely tiny. And if you let this guy go to 0, look at what you have. A sub 1 over 1 minus r. That's the formula for finding an infinite sum. For an infinite geometric. This is the only kind we can find the sum for. Reliably. There is a sum only if this common ratio has to be less than 1. Now, the reason I put that in absolute value bars is because I don't care if it's positive or it's negative. Ignoring the positive or the negative sign, his value has to be less than 1, because that's what allows this term to go to 0. And if I'm going to effectively at some point be adding on 0, it would make sense that I can find this sum. So this is your fifth and final formula for working with arithmetic and geometric sequences. It is the formula for finding the sum of an infinite. Some instructors will even put, most authors don't, but they'll sometimes put a little infinity sign underneath there just to kind of remind students this is the sum for the infinite geometric. And you'll notice it's a very nice, easy formula. So let's go back to that, the medication one. The very first term was 20. 1 minus, my common ratio was 1/2. So we get 20 divided by 1/2, which is 40 milligrams. It's actually a very interesting idea. If you know that the body is going to metabolize 50% of that pretty reliably along the way, then you would expect no more than 40 milligrams of that medication to be in the body, no matter how long this person is on the medication. And it was interesting if you go back and look at our sequence of the partial sums, technically, the sequence of partial sums was 20. And then how much was in the body on the second day? I'm adding up first day and second day, and then 35, and then we had 37.5, and you can see that it's getting ever closer to that 40. Okay? I think that's a pretty interesting problem. Now, let's do some practicing. You've got 3 different formulas now to be working with, and those are for geometric, so we do want to make sure that that's what's happening here. On this very first one, and again, this notation is just, pretty high level, but you know it. The sum, as k goes from 1 up to infinity. As soon as I see that, I think, I hope that this is geometric with a common ratio less than 1. Of course, if it's not, chances are this sum is going to infinity in what you're doing. Don't use that strategy in Calc 2. All right. Well, let's write out a few terms. I always recommend that so that you know what's happening. If k is 1, we have 5 over 3. Why did I put the plus sign? I put the plus sign because of the sigma. If k is 2, I have 5 over 9. If k is 3, I have 5 over 27. And that's supposed to go on just forever. Now, do you think I'm adding to get from term to term, or am I multiplying? Well, you might see that this is times 1/3. Times 1/3. And again, it makes sense from the formula. But I do suggest, even as you get stronger and stronger in these, write out several and verify it for yourself before you go on. So in fact, this guy is geometric. His common ratio is less than 1. He's going to infinity. So I'm going to use the formula a sub 1 over 1 minus r. Okay? So my sum is 5/3 over 1 minus 1/3. Where did I get the 5/3? Where did I get the 1/3? The 5/3 is the first term. The 1/3 is my common ratio. Okay? So I end up with 5/3 over 2/3, which is 5/2. Okay? Now let's write out some of this. Again, it's kind of scary. I'm going to infinity. If k is 1, I get 1 over 7. If k is 2, I get -1 over 49. If k is 3, I get a +1 over, well, I do know 7 cubed is 343, but you might want to write it as 7 cubed. And you might want to think of this as 7 squared. It might help you see what's going on. Oh, okay. I am multiplying each time times -1/7. So I again can use my formula for the infinite sum. It's going to be first term, which is 1/7 over 1 minus the common ratio. Well, that ends up being 1/7 over, what, 8/7? Isn't it amazing? We just added up infinitely many fractions. And you thought adding 2 fractions was hard. Adding up infinitely many of those, the answer is 1/8. Okay? Now, you might think this is totally off the subject. Write a rational representation, means a fraction, for 0.9 repeating. And you might say, how does that fit in? Well, that whole ... there is a little bit of a hint. And then you think, well, if I was going to write out 0.9 repeating, that would be 9/10 plus 9/100 plus 9/1000 plus, oh, you see the pattern going there? That's kind of sweet. And so, let's see here. What are we multiplying by to get from term to term? Isn't it 1/10? Times 1/10? So we have an infinite geometric series, and it is first term over 1 minus the common ratio of 1/10. And looky there. We end up with 9/10 over 9/10. The rational representation for 0.9 repeating is 1. Okay. Well, just a few more. Oh. What's different about this guy? You might say, well, you stood that infinity sign on his end. Yeah, I made it an 8. We're going from 1 to 8. So does that mean we get to use that nice simplified formula? No. Okay, let's write out several terms. If k is 1, we end up with 3 over 4. Do you know where I got the 4? 2 to the -2? Okay. Now, if I put in a 2, I get 3/2. And if I put in a 3, I get a 3. Now, I only have 8 terms here, but that's okay. I don't want to keep writing them. Do I see the pattern? Do I see what's happening here? And again, this rule kind of gives me a huge hint as to what's happening here. I'm multiplying by 2, multiplying by 2. Now, this is a finite sum. So to get this finite sum, I have to use the more complicated formula over here. Remember, the a sub 1, parentheses, 1 minus, common ratio to the nth. Yeah, I know, he's not fun. First term times 1 minus my common ratio. Now, what will the n have to be here? I'm trying to add up the first 8. So it's 8 over 1 minus the common ratio. And I think I'll just leave it there. You could run through the arithmetic on that. Okay. On this guy, notice I started at 0 this time instead of at 1. So my very first term is 10. And then when k is 1, I get 20 over 3. And when k is 2, I get 40 over 9. And how far am I going? I'm going to infinity. Does this qualify for using the formula for an infinite geometric? He's geometric, he is infinite, and the common ratio, what's being multiplied each time, is this 2/3. So it's 10, first term, over 1 minus the common ratio of 2/3. And I believe that ends up being 30 rather easily. Okay? Now for this last guy, let's write out a few. Put in a 1 and I get 1. Put in a 2, I get 3. Put in a 3, I get 6, I get 5. Is that geometric? Well, I'd multiply by 3. Is he arithmetic? I'd add 2, add 2. Is the next guy 7? Yeah, he is. Oh, I pulled a slick one on you. This guy is not geometric. That's why you've got to take some time and, write these out, take a look at them. So then I want you to go back and look at how do I find the sum of the first 50 terms of this arithmetic. And that's why in our summary here, I said make sure you practice both types. You might want to put some on index cards, some arithmetic, some geometric, so you mix those up. And you have to look at them and first decide, is this guy arithmetic, is he geometric, or heaven forbid, is he neither? Okay? Now, in the case that he is geometric, to get to the nth term, you have a formula. For a finite sum, you have a formula. And for the infinite sum, the only infinite sum we can find at this point in your development is with our geometric when the common ratio is less than 1. Practice, 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 and remember to mix up your problems so that you get a really good handle on what's happening with your sequences and series. I'll see you in the next lesson.